Howdy, my name is Mike. This is going to be my final geography presentation on how heat makes weather. This is a very lengthy topic, so I'm going to try and keep it under 10 minutes here, and we'll just get right into it. So my table of contents, this is me what we're going to be talking about. So it's going to be how pressure and heat are correlated, how heat and density are correlated, how Earth is heated and how it's unevenly heated, how pressure affects weather and creates our weather systems, other effects on weather such as topography, moisture and humidity, and the Coriolis force. And then we're going to bring it together at the end and then talk about how global warming changes our current weather. So to start off, how heat affects pressure. So heat and pressure they have a strong direct correlation. So what that means is as pressure increases, heat increases, and as pressure decreases, heat decreases, and vice versa. They affect each other, and they cannot be excluded from each other. The way this happens is when you have all your molecules here, all your particles of either gas or liquid or solid, but in this case gases, when they have very low energy, when they're very cold, they're stationary. They don't move around a whole lot. And that's why when things get very cold, they freeze. But as you introduce more energy, they begin to shake around, they begin to vibrate, and eventually they start to bounce around. And this is, in this case, a closed container. But as they start to bounce around, they hit each other and then they hit the edge of the container with a lot of force. And this force, this energy, is what we consider to be pressure. So yeah, when something's high temperature, it's high energy, and that means it's high pressure as well. Additionally, heat and density have an inverse correlation. It's very strong, but it is an inverse correlation. So what that means as a gas increases in temperature, it decreases in density. And so that's why hot air rises and cold air sinks. It's because it's less dense. Hot air is less dense, so it literally floats to the top of the air. And what this can cause is the mixing of hot and cold air. As hot is rising and cold is sinking, it can mix and it can cause something called unstable air. Unstable air is how we get thunderstorms, is how we get tornadoes. It gets, all that good stuff. And then we're going to talk about how Earth is heated, because Earth is not heated evenly. This is a huge part of our weather system. This is actually the main part of our weather system. So some areas receive more sunlight and are heated more. Areas around the equator are going to be receiving that direct sunlight all year round. And so areas on the poles are only going to receive that direct sunlight sometimes. They're going to receive less direct sunlight. This is due to the axis of Earth, and this is what also causes the seasons. Earth is on a tilt here along its axis, and as you can see, during those June, July, August months, the northern hemisphere is being heated much, much more. It's getting more of that direct sunlight. And then coming over here on those December, November, January months, the sunlight's hitting from this side, from the position around the sun. And so the southern hemisphere is going to be experiencing those summer seasons. Additionally, different surfaces are heated differently. This is partially due to the texture of them and some other factors, but a big part of this is the color. As you know from wearing a black shirt out on a sunny day or a white shirt out on a sunny day, these reflect and absorb differently. Those darker surfaces are going to reflect, or are going to absorb more energy and reflect less, while those lighter surfaces are going to reflect much more. And the reason this is important is any light that is not reflected back into space is instead going to be turned into thermal radiation, is going to be heat. And so when we're talking about darker surface, asphalt's a very, very good example. If you've been in a big city, it's much hotter there than the surrounding fields. Additionally, the ocean, not so much the Arctic Ocean as much as the, tropical equator oceans are going to have that darker water that's going to absorb a lot more heat. On the flip side of that, these sort of tan white grasses that you see in a lot of fields and tundras are going to reflect a lot, and then clouds and ice caps are nearly pure white, and they're going to reflect a lot of sunlight before it can be turned into that thermal radiation. Next, we're going to talk about how pressure affects weather. The big thing to know with this is gases move from high pressure to lower pressure because they're trying to equalize. Air very much likes to equalize. Think about when you are using, a syringe to drop fluid. You're creating that area of low pressure and something has to fill it. It really wants to fill in that area. And the other thing to note with this is when hot air rises, it leaves an area of low pressure. It's moving from that space and they need something to fill it in, so it creates low pressure. When cold air sinks, it creates high pressure. That sinking air packs in the air and it becomes very, very dense. Very, very high pressure. Not dense. As you can see from this diagram here. There are many other effects on weather, but I believe these are the three most important, so I'm going to go over these three real quick and talk about some of the other reasons that our weather system is the way it is. One is terrain. Terrain is the physical disruption of airflows. You can see this with everything. Everything affects it, even smaller things like buildings, that sort of thing, but the main things you're looking for are mountains, lakes, and oceans. A big part of the physical disruption is the friction. The friction starts to kick in about 100 feet to 500 feet above Earth's surface, where it starts to affect the air. And this is usually enough to counteract the Coriolis effect. And so when you're coming in, especially here in either the Colorado Springs airport or the Denver airport, where we have lots of mountains, that sort of thing, you will notice there's a lot of turbulence right before landing. That's because of this friction. It can also cause things such as upslope fog, where when humid, warm air is pushed up a slope by wind, it cools down and then condensates into that fog. You also see this valley wind, where you have a valley with cold air sinking as night falls, and then it literally flows like a river down through the valley. It's very, very cool. The other big effect is moisture. Humidity is the amount of water in the air. This can be affected by nearby water. If you've ever, stayed by a lake, stayed by an ocean, you know it's very, very humid. But water can only hold a certain amount. Cold air holds less, warm air holds more. So down by the equator where it's very, very warm, it can be very, very humid days because it can hold a lot of that humidity. But up here and further north here, we usually have very dry air because we have cold air and there's not a lot of, it can't hold water even if there is water available. When the maximum amount of water is reached, which is called the dew point, there has to be visible moisture. It can't stay invisible anymore. And so that either condensates and stays in the air, such as fog or clouds, or it precipitates and it turns into rain, snow, or hail. And lastly, this is a very, very long topic, so I'm just going to touch on it, but the Coriolis force. This is the force caused by the rotation of the Earth. Earth spins and causes this force. In the northern hemisphere, this causes a deflection to the right, or the clockwise direction. In the southern hemisphere, this deflects to the left, or counterclockwise. This is responsible for air currents, ocean currents, and cyclones. So this is essentially any of our currents. This is why it happens. And now this isn't going to happen on a small scale. You won't see this in your sink, but when you're talking about massive moving air and water currents, or aircraft traveling through a very long distance, it's going to have that. So the important thing to note is gases and liquids, because of the Coriolis force, do not move in a straight line. We talked about how air wants to come into these low pressure systems, but it can't do so in a straight direction. I apologize for this arrow. This is pointing the wrong way, so I apologize for that. But it has to come in, and this is demonstrating the normal hemisphere, and as it does so, it spins. And you start to see the spinning movement of this air mass. As it begins to spin, that's how we get cyclones. That's how we get hurricanes. Oh, and one more thing to note on. That's additionally the reason hurricanes can't cross the equator, because the Coriolis is in different directions. And it's also why we tend to see a line of clouds right along the equator. So to bring it all together, the interaction of all these systems is what creates our weather system. And it is a very balanced system, a very delicate system. And the important thing to note, it only relies on one input. The only input that can change is our heat. It's the heating. And so nature and humans have evolved and adapted to this delicate cycle. If this cycle were to change, it wouldn't have any effects on the Earth per se, but it would affect the plants, animals, and humans living on the Earth. And that's the important thing to note. As we go into our final slide here, current global warming and climate change. We need to think about how our global warming currently is affecting our weather system and how it's doing that. Higher temperature means more energy in the system. We just physically have more energy on our planet right now than we have in a very, very, very long time. And this can lead to some obvious things. This can lead to high temperatures, of course, and it can also lead to droughts because that water is getting evaporated. There's less precipitation in some areas. And that's one of the more obvious effects. But perhaps one of the less obvious effects is warmer air means there's more dramatic rising, cooling, and sinking. With warmer air, we get more of that unstable air as all of this air parcels are interacting. And this unstable air and more dramatic pressure systems can lead to more cyclonic activity. So that means more storms, more, tropical depressions, that sort of thing. And so I pulled this data. This is from the EPA from this year. And this is just the current tracking of cyclonic activity and cyclonic power. And so as you can see, if you just track this, it's very up and down, but it is a increase in correlation there. It's less obvious to see here. We have these higher days here, but the general trend is up here as well. And so when we're thinking about reasons to be considering lowering our global temperature through whatever means possible, I think this is a very good thing to consider. These storms, although we are adapted to them, they are very, very cataclysmic for a lot of people. And if we were to see even a 10-20% increase in the storms, it would not only mean destruction for many, many natural ecosystems, but it would also put many people's lives on the line. It would cause a very, very high financial crisis with the amount of damage that it's causing. So I just think that's something worth considering if you're not fully sold on reducing global temperatures and trying to put a stop to global warming. I think this is a good thing to consider. So with that, I hope everyone has a fantastic winter break, and thank you.